We're going over in this video the solutions for the June 2016 S2 paper from Poisson's Edexcel. We'll start off with question 1, just some summary data here, and they ask us, so it's actually real data, it's not a model, it's actually something that's been collected. And they want us to work out the mean and variance, so that's something that we did in S1. So the mean is equal to the sum of all the values times by divided by the total number, and the total frequency here is all of these numbers added together, which we can see is 100. Okay, so that's, and the sum of them, if we add all of these together, we've got, well, let's just put the calculation in. It's 1. You might choose to put them into the stats mode of the calculator as well, but I still would write out at least the summary data. You'll find that so long as you write sigma x in, having used the stats mode of your calculator, you're fine. But I'm going to do it without doing that, or at least show my working on how we got that. So 0 times 24 plus 1 times 37 here, plus 2 times 21 plus 3 times 12 plus 4 times 4 plus 5 times 2, and I'm going to leave the 6th one out because that's confusing, but thankfully there's none of those, over 100. The top totals to 141. As I say, it's fine to use summary statistics, but if you are going to use the stats mode on your calculator, I wouldn't just go straight to to the mean x. At least tell us what the sum is, and the stats mode on your calculator will give us that. So that's 141 over 100, which is 1.41 exactly. Right, now the variance is equal to sigma, or we might as well put the f in it, the f in the formula, is fx squared over n minus the mean squared. So that will be equal to 24 times 0 squared from those two, and then 1 squared, 37 times 1 squared, and then 21 times 2 squared, and 12 times 3 squared, 4 times 4 squared, and 5 times 2 times 5 squared, all over 100, take away 1.41 squared. And when we work that out, that gives us the variance is equal to 1.4419. So we can round that if we want to 1.44. So that's part A done. Part B wants us to explain why Poisson is justified. Poisson is a good model if the mean and variance are the same, and they are approximately the same here. So we can just say the mean is close to the variance. That in itself is enough to suggest a Poisson is a good model. Okay, so now we are told that this is Poisson with mean lambda 1.5 per number of cherries in a fruitcake, 1.5. So we've got lambda equals 1.5. So we've got the probability of getting x equals to 2. We can use tables to do this, but because it's one single value, I'm going to use the formula. So that's e to the power of minus lambda, and lambda is 1.5 here, times by 1.5 to the value of what x is, which is squared, divided by the value of x factorial, and that comes to 0.2510. It can be got from the tables, but I haven't. It might be worth using the tables as a check. That's part C1. Part C2, I would use the tables here because it says at least one cherry. That means it's got to be at least one cherry. So that's, well, actually I wouldn't use the tables here either, because we've got probability that x is, it's got to be 1 or more, so greater than or equal to 1, at least 1. It's easier to do 1 minus the probability that x equals to 0, so I would use the formula here again, which is 1 minus e to the minus 1.5. Although we could, to be honest, it's not worth bothering opening it. In my book, it's not even bothering opening the formula book, but it would be a useful thing as a check at the end of the paper to use the formula book, because whatever the value for naught is will be whatever this is in the formula book. So that's 1 minus 0.2231. That will be our form. That's the number we'll see in our tables. Anyway, the final answer is 0.77 to 4 significant figures, 69. Okay, so that's part C done. Right, now we've got some variations on that stuff. Okay, so it says here, it talks about 5 packets of these fruitcakes, and in one of them the mean is 1.5. I must admit, when I first read this, the first sight was thinking binomial, because it feels like it's a fixed number of trials, but actually that would be incorrect, because all the 5 does means that we've got basically 5 times the amount of cake, so the rate will be 5 times the amount. That's it. So we're going to just say that this time, let's call it y, is Poisson 5 times 1.5, which is 7.5. So that's the distribution we're dealing with. Okay. So now we can say the probability that y is greater than or equal to 11 equals to 1 minus the probability that y, because it talks about more than 10 cherries. So that means it can be 11 or more, but not 10. So be careful with your inequalities here. Okay, so that's giving us 1 minus probability, all of the ones up to 10, so that's x is less than or equal to, y is less than or equal to 10. And now, of course, that's essentially the summation of 11 different uses of the formula, which would be too long. So now we really do want to be using the formula and finding this number in the formula book. So let's just open the formula book. Right, so this is page 26 of the formula book. So it's the 7.5 here that we're looking for. That's 7.5 because lambda is 7.5. Okay, and then we want the value for 10. So it's this number here, 0.8622. So let's put the 0.8622 here. And that gives us and thankfully they've given us the answer on this, so we have that kind of warm feeling that we really do feel that we're right on this because it told us to find. Well, I've said that my gut feeling was that this is binomial at this point because I saw the 5 trials and I was wrong. But then we do have one where it looks that it is binomial, and they do like to mix these questions up so that they're testing what your actual understanding of when it is a binomial or Poisson. And this now is binomial because it's saying 12 packets of raised fruitcakes are selected at random. Well, we've got this one packet has got 5 cakes in it, but that's now irrelevant. We know that one single packet has a probability of this number here that we've just worked out. That's why I think they've given us the answer, so we can take it to the next bit. Maybe worth a hint, if they give you an answer in stats exam like that, the chances are you're going to use that in the next bit. So it's this number that's key, because that is going to be the probability that there are more than 10 cherries in total. And here we want the probability that out of 12 of them, 3 have got more than 10 cherries. So let's call the distribution something different that we haven't done, a letter we haven't used yet. I don't really want to use Z. I'm going to use W. W is a binomial because we've got 12 of them, and the probability that any single one of them has got more than 10 is 0.1378. So we're looking for the probability that W equals 3, because it wants exactly 3. So if I said more than 3, exactly 3. So we want W to be 3. So we're just applying the binomial formula now. That's 12C3, because 3 we want 3 out of 12. 0.1378 cubed, and I've got the other number I want here, 1 minus it, 0.8622 to the power of 9, because we've got 12 trials in total. And if we work that out, we've got 0.1516. Okay, that's first question done. Let's get on to the second question. Okay, so we've got looks like another binomial or maybe significance testing question here. It says in a random 5% of people have red hair, and in a random sample of n, we know that the expected number is 3. Well, the one thing about the mean is that NP is equal to the mean, or EX is equal to the NP for the binomial. So we have 3 is equal to n times by 0.05. So that gives us, for part A, n equals to 3 divided by 0.05, which is equal to 60. Nice easy 2 marks there. So then it says a random sample of 20 people is taken from this region. Find a probability that exactly 3 people have red hair. So that's not going to challenge us, I don't think. We've got, let's call it R, because for red hair, let R be the random variable, be 20, and the probability of excess, probability that they do have red hair, is 0.05, and we want to find the probability that R equals to exactly 4. So applying the formula, that's 4 out of 20 successes The probability of success is 0.5, so that's to the power 4. The probability of failure is 1 minus that, which is 0.95, and that is to the power 16. And if you put that into your calculator, you'll get 0.0133 to 3 significant figures. Okay, so that was pretty straightforward again. So second part, it says at least 4. Now let's get the inequality right. That means 4 or more. So we're being asked for the probability that x is greater. Let's go to R. It doesn't matter if you call it x or what you call it really. So R is greater than or equal to 4. Now in order to adjust it so that tables can be used, we can say that 1 minus the probability that R is less than or equal to 3. Okay, and now we're going to go back to the tables to find that number in our tables, because it really, otherwise we're going to have to add 4 binomials together, 0, 0, 1, 2 and 3, so it'd be quicker to use the table. So let's pull up the tables again. Now we're looking for 20 trials here, so we get up to 20. We've got n is 12, n is 15, n is 20. So here we go. So here is the number we need to pull up now, because it's 3. The probability, so that what that's doing is it's adding all the ones 0, 1, 2, 3 together. So it's 0.9841. So that gives me 1 minus 0.9841, which gives me the answer 0.0159. Okay. Right, okay, so that's part B done, both parts, and now we've got a bit of significance testing, a bit of hypothesis testing to do here. It says Patrick claims that Redmond people have probability greater, it's a key word because that points to a one-tail test, and 5% of having red hair. In a random sample of 50, so that's another key thing, 4 of them have red hair. Now, whenever they give you the value of a test statistic, I rather use that than work out the critical region. You can work out the critical region, but it's generally easier to work out what the probability of getting that number, or something even a little bit surprisingly more than that number, because what's noticeable here is that out of 50 we would expect, normally we would expect out of 50, because the mean is 0.05, we would expect 50 times 0.05, which comes to 2.5. Now we've got more than that. So a little bit, not doesn't feel significant to have to say, but we've got more than that. So what we have to do is test that we get 4, or something even a little bit more surprisingly more than that, 5, 6, 7, up to all the way up to 50. So set the 4 or something even more remarkable than 4. I must admit 4 itself doesn't feel that remarkable, and this does not feel as though it's particularly significant, particularly at a 1% level. Now, notice we've got percentage here, which isn't the significance level, so watch out for something like that. It'd be so easy to read the 5% as though that's what the significance level is, but the significance level is 1%. So let's set up our hypothesis. We know that it's, let's let x be a binomial with 60 and not 60, that was from before, 20 and some value p, unknown. The null hypothesis is that p is not changed from what we had before, so the probability is 0.05. We don't think it's changed. up for the null hypothesis, and then the alternative hypothesis is greater, and it's one-tailed. We haven't been asked for a probability of a change, so that's that p is greater than 0.05. Okay, so what we do is we work out the probability that x is this number, this value of the test statistic we had, plus something even more surprising, if you like, greater than or equal to 4. Given that, assuming that our probability remains unchanged. And what happens is, if this number becomes below our 1% level, then we reject H0, but I don't think it will. I think we'll be accepting H0 here, but anyway, we'll see. So probability that x is greater than or equal to 4, that gives me, let's just do that, that's the same as 1 minus probability that x is less than or equal to 3. Okay, so that's, oh wait a minute. Just a sec, I noticed a mistake there. I said 50 and then I said 60 first. It's 50, of course, for our number of trials. So anyway, we need to go back to our tables again. So that's x less than or equal to 3 is the number we need to find in our table. So let's just go back to tables. So we're looking for 50 trials now and the value of 3. Yeah, there we go, 0.7604. So that's 1 minus 0.7604, which is equal to 0.2396, which is greater than our significance level, 1%, 0.01. So that means that we accept H0. Okay, there is insufficient evidence, and we need to write in the context here, is insufficient evidence to suggest that people in this town have a probability greater than 5% of having red hair. You need those words, you need to mention the original context, and you need to bring it back to the context of what you actually put it in. So just saying accept H0. So you can say not significant if you want as well, just to kind of run the point home. It's not significant, I mean, it's not very, you can say it didn't feel as though that would be significant, because the mean was 2.5 and we got 4. Anyway, that's question 2 done. Let's have a look at question 3. Okay, so this is a continuous uniform distribution. This one goes between 5 and 9. Rather than just remembering the formula, stands to reason that the probability, that must be a quarter there, because the area underneath has got to be equal to 1. So my PDF, we're making us work for our 1 mark here because it says specify fully. So we need to write FR for the radius, or the value R there, FR equals to a quarter if our value of R is between 5 and 9, or 0 otherwise. Okay, and then another easy 1 mark. It says find the probability that it's between 7 and 10. Well, look, between 7 and 10 effectively means between 7 and 9 here, because it can't be more than 10. It means this area here. So that's definitely equal to a half. So the probability that a random variable is between 7 and 10. I've written the inequality differently here, but I don't really care because it's continuous. It should be the same. I'll try and rub it off just to be consistent, but it actually doesn't make, because it's a continuous distribution, we can be a bit lazy about what kind of inequality we use, but I don't annoy anyone, so I'll use the same one as the question. So that's 7, 10 equals to a half. Right, so part C, it says the random variable A is the area of a circle. We know what the area of a circle is. A is equal to pi r squared. So we want EA is equal to pi times ER squared using combination of random variables. Now, we've got 2 choices for working out the ER squared. We could either work out ER squared from from integration. Okay, we could work that out using the integral of ER. So we would be doing summing that over a certain amount, but I'm going to do using a very handy fact about variance, because we know the variance of R equals to ER squared. Let's be consistent with my R's here. Minus ER. Okay, so we want ER squared, and we know ER. Because ER is going to be equal to 7 because it's halfway along. So we can say that ER squared equals to the variance of R plus the mean of R. Now there is a formula for the variance of R, which is actually given in the formula book. I'll just go and show it you now. Okay, so here it is, 1/12 b minus a. Okay, I meant 1/12 b minus a squared. But anyway, our numbers are 9 and 7, 9 and 5, so that's 1/12 of 4 squared plus ER, which is clearly 7. Okay, so that gives me, I just obviously forgotten to put the squared on there, which is a bit bad. So that's equals to that, and that comes to 50 over 3, 50 and a third, sorry, which is equal to 151 over 3. So let's go back to now we can go to the EA bit is therefore equal to pi times 151 over 3. And that comes to 158. Okay, apologies for the slight ramble there and getting the formula wrong for variance. You can do by integration as well, and that might be a useful check if you did it this way. Some people prefer to do by integration. Okay, let's look at the next question. So in this question, it's PDF-CDF question. We're given the CDF with a various number of unknowns, and we're given a bit of information about it. We're given the fact that the mode is 8 over 3. Well, we can work out the CDF by differentiating this. I'm not going to fully specify it. All I want is the rule bit for it in the middle. So I can differentiate that, because remember, small case f for CDF. If I differentiate that, we've got kx differentiated, which gives me ka. We've got the kb squared differentiated, which is 2kbx. And the kx cubed differentiated, which is equal to minus 3kx squared. So that's some kind of PDF, so it's got a quadratic in nature. And we have told the mode. Now the mode is gained from the maximum point, or the highest point of the fx, of the PDF. Now, we shouldn't assume always that it's some turning point, because, for example, if we had something like this, it's not a turning point, the maximum point is there. Or even like this, if we had a PDF like that, then the maximum point would be here, would be at the end. But in this case, there's a lot of information, because the mode is lying between, it's quadratic, and the mode is lying between our 2 points, 2 and 3, in between somewhere. We can, in this case, assume it occurs at a minimum point. So all we have to do is differentiate. So let's just write f stroke x. The ka bit is going to disappear, and we're going to get 2kb minus 6kx. Okay, and it's because we know the mode is 8 over 3, we can just equate that to 0 and get our b from this. And we don't have to do anything else. Because, of course, what a lot of people apparently in the exam did is totally plough on with the fact, which is going to help for part B, that f0 equals, not f0, f2 is equal to 0. And f3 equals to 1, but we're going to use that for part B. We don't need it for part A. We're just using the fact that the mode is 8 over 3. So we know that f stroke 8 over 3 is equal to 0. So we can say that 2kb minus 6k times 8 over 3 equals to 0. And that's going to, the k's cancel, and we just get 2b equals to 16. So that gives us b equals 8 as required for part A. And then for part B, as I've just alluded to, we're going to use these two facts to work out our k and our a in the other 2 bits. So we're going to use the fact that f2 equals 0 first. So f2 equals to 0. We now know that b is equal to 8. So we've got f2 equals 0, so we've got k times by a times by 2 plus b, but we know b is 8 times 2 squared minus 2 cubed equals 0. Now, of course, in this case, the k cancels. We can just divide by k. And we get 2a plus 8 times 4, which is 32, minus 8 equals 0. So 2a is equal to minus 24. A equals minus 12. This has come out quite nicely because we don't end up with simultaneous or anything when we do it nice and in order. So we've got A is minus 12, so we've knocked off, we now know what A is and we now know what B is. And as I've said before, we can use the fact that F3, because all the numbers are at least less, the highest it can be is 3, so it's absolutely certain that any particular number will be less than 3, which is what F is. It gives a cumulative. So F3 equals 1. So I can say that K times by A, which is minus 12, times by 3, plus b, which is 8, times by 3 squared, just put it into here, minus 3 cubed equals to 1. So that gives me k, that's minus 36, plus 8 times 3 squared, that's 8 times 9, which is 72, minus 27 equals 1. 72 minus 36 is equal to 36. And then take away another 27, that's 9. So we've got 9k equals 1. So k equals to 1 over 9. Okay, so that's it for question number 5. So question 5 of the June 2016 S2 paper is a bit of an unusual question where it's talking about a normal approximation to binomial. But we're working backwards and finding n. Obviously Edexcel are trying to get imaginative about how they might make the questions a little different. So this one feels a little bit weird, but we'll get on with it. We've got an unknown n, but we're told that the probability is 0.2. Now, of course, we need the mean and variance of those if we're going to apply a approximation. So the mean is equal to np, and that equals to 0.2n. The variance, or the standard deviation squared, is np 1 minus p. So that's equal to n times 0.2 times 0.8. So that's 0.16n. So that's the variance. The standard deviation is the square root of that. So that's 0.16, the square root of n, which is 0.4, the square root of n. Writing like that would probably be more helpful using search. Okay, so that's our standard deviation for our thing. So we're using, let's call y our normal distribution, with mean this, which is going to give approximate values for the binomial of this, is 0.2n, and standard deviation of that, but we normally write it like that, don't we? Variance. So that's our normal distribution that we're working with. Now let's apply this, what we're given, because we're told this is a value that we're given with the normal approximation. So we're told that p, first of all, let's just start with the original binomial. We're told that what we're trying to work out is probability of x being greater than 55 is equal to, now using, what I tend to do is like to try and change it to a strict inequality, a non-strict inequality first. That, okay, and using the continuity correction, once we've changed to that type of inequality, not the strict inequality, the way I work out the continuity correction is to use a number line. We've got 56 here, 57, so that on the number line would be there for, and we always extend backwards if we're applying the continuity correction. 55.5, so we go kind of back from the number line, but that's only if we've made that adjustment to a non-strict inequality like that, so you're kind of always making it bigger. So that means it's approximately, it's like the approximate probability of y being greater than or equal to 55.5, and that's what we're actually told. We're actually given this bit of information, so we're told the probability y is greater than 55.5 equals to 0.401. Okay, now we're going to be using the tables here at some point, so we might choose to change that. We'll change it to Z first of all, and we can always do that in a moment. So that gives us, no, let's change it now. I keep changing my mind. Okay, so we've got this area here, we're told is 0.0401. So if this area here will be 1 minus that. So probability that y is less than or equal to 55.5 is equal to 1 minus 0.1 minus this number, 0.401, which is equal to 0.9599. Okay. Now what we do is we change to the standardized normal distribution, where z is equal to the mean, mu, take away, the value x or y, in this case, take away the mean divided by the standard deviation. So we have the number that we're looking for, probability z, is less than or equal to y, which is 55.5, minus the mean, which is 0.2n, divided by the standard deviation, which is 0.4, the square root of n, is equal to 0.59599. Okay, so now we're looking for the appropriate number in our tables. So let's just go to the tables and look for this number in our tables, and I suspect it will be actually bang on because of the nature of the question. So let's have a look at the tables. Yes, indeed, if we look at the normal distribution tables, we can see the 0.959 there, which indicates a z value of 1.75. Okay, so let's go back to the question. So basically, we have we know that this number is 1 of the z thing here, where that's we know the number is 1.75, where this is 0.9599. So basically, we know that this is 1.75. So 55.5 minus 0.2n over 0.4, the square root of n, is equal to 1.75. So if we turn to solving this equation and multiplying out, minus 0.2n is equal to 1.75 times 0.4, which is 0.7, the square root of n. Let's bring it all over to one side. 0.2n plus 0.7 the square root of n minus 55.5 equals 0. So I'm going to times this by 10. 2n plus 7 the square root of n minus 555 equals 0. This is basically a disguised quadratic. If you want, I'm not going to, but if you want, you can let square root of n be equal to a or x or whatever, and then it becomes 2a squared plus 7a minus 555, and you have to solve that and then take the square root of it. But I'm going to put it straight into factors here. You can use a formula, but because I'm pretty clear that it's going to be a whole number, I do like to try and factorise if I can. You might have noticed these numbers here that just suddenly appeared. That's me playing and trying to find out the factors. I found that 37 goes into it and then I divided by the 5 and the 3. So 15 and 37 look pretty promising because we want to aim to the 7 and they do. Because if we have, this will be the square root of n there and the square root of n there, and 15 and 37. I think this may get us what we want. We'll have a plus there and a minus there. So that gives us the square root. This one obviously can discount, so we have the square root of n equals 15, so n equals 225. Okay, which is a kind of number we might expect it to be. We'd expect it to be large. Okay, a bit unusual. Let's see if whether question 6 poses any such surprises. So it looks like a pretty regular sampling distribution question. Is question 6. First, we've got certain number of counters with numbers on them in a particular ratio, and it wants to find the sampling distributions of means of them eventually in part B. Part A is just to list all the possible sample sizes of 2. Well, of course, you could have 2 4s. Okay, we could have a 4 and a 6. Now the order isn't important here in terms of what's actually in the sample. So 4 and 6. Could also have 4 and 8. That's all the ones with 4. So we could then have 6 and 6, or 6 and 8. And finally we could have 8 and 8. So that's part A of the question done. Okay, pretty straightforward part A. Part B is to ask him for the random variable m represents the mean of the 2 counters. Find the sampling distribution for m. Well, we can, if we work out what the mean is of these numbers, the mean there is 4, the mean there is 5, the mean there 4 and 8 is 6, the mean there is also 6, the mean there is 7, and the mean there is 8. So if we call these means x bar, and for some reason they've called the thing m, which is a bit confusing because it's often means mode, but let's stick with the strangely in their own mark scheme they've gone back to x, but anyway they've called it m in the question, so we'll call it m here. So these are the possible values: 4, 5, 6, 7 and 8. It actually gives the values for 4, but let's work them out anyway, because of course the probability with one sample, because we've got the ratios here, we've got the probabilities of getting 1 4 is equal to a half, because that's 5 out of 10. The probability of getting, in a sample of 1, a 6 is 3 out of 10, and of just taking 1 of getting 8 is 2 out of 10. So the probability of getting 4 can only be of getting a mean of 4 is that only if we've got 2 4s, and that will be half times a half, which is a quarter. Probability of getting a 4 and a 6, which would lead to a mean and a 5. Well, there's two different ways of doing that, because it can come out in two orders, 4 and 6, and then a 6 and a 4. But then we've got the 4, which has got probability a half, and the 6, which has got probability 3 over 10. So that's equal to 3 over 10. So that's half, and this is 3 over 10. 6, now we've got two ways of getting that, so let's work them out first of all. The 4 and the 8, again there's two ways of getting a 4 and 8. It's either 4 and 8 or an 8 and a 4. Again, the probability of getting a 4 is a half, and the probability of getting an 8 is 2 out of 10, or 1 out of 5. And that cancels out to be 2 out of 10. The probability of getting a 6, though, of getting a 6 here with two 6s here, that's equal to 3 out of 10, or times 3 out of 10. There's only one way of getting that, because it's just 6s, which is 9 out of 100. So it's these two added together. So that's 20 out of 100 plus 9 out of 100, so that's 29 out of 100. Okay, then there's 6 and 8. That's, again, two different ways of getting that. And the probability of getting a 6 is 3 out of 10. And the probability of getting an 8 is equal to 2 out of 10. 1 out of 5. So that comes to, and they both cancel out, I think that cancels out to 3 out of 25. So we've got 3 out of 25 there. The 8 they've given us is 1 out of 25, but it's basically a result of the 2 out of 10 times 2 out of 10, or 1 out of 5 times 1 out of 5, because there's only one way of getting that, which is 1 out of 25. I would check, when I've done a sampling distribution in this way, that these numbers add up to 1. If we change the denominators to 100, this one here, that's 4 out of 100. This one's 12 out of 100, so I'm up to 16 out of 100. Then we've got 29 out of 100, so that's 45 out of 100, plus another 30 out of 100, which is 75, plus the, just good, so I can check my answer. That should be a quarter, which is a number, which is 25, so now it's right. So, just straight, because it told us a quarter there, so I don't know why I wrote half there, but anyway, we've resolved it in this quarter. Okay, so that's part B done. Part C, right, this is the kind of thing they like to do, is they like to throw something slightly different in with a different type of distribution or whatever. It says a sample size of n sets of 2 counters is taken. And so the fact that it says a fixed number of n sets with 2 counters is taken, it talks about having a mean of 8. So that basically means it's binomial with some number n, and the probability of getting an 8, a mean of 8 here, is 1 out of 25. Okay, and we're told that the probability that y is greater than 1 is going to be greater than 0.9. We can write that as probability of 1 minus y equals to 0 has got to be greater than 0.9, and rearranging that gives me the probability of y equals to 0 has got to be less than 0.1. Okay. Now y equals to 0, this is binomial. So if there's no successes, that means that means that we've got n lots of 1 minus that, which is 24 out of 25. And they will allow you to use trial and error here, but I'm going to use logs. If we take logs both sides, let's go up to here. If we take log of 24 over 25 to the n, has got to be now it's a bit funny with the inequality here. They'll probably allow you to use an equal sign, but actually the inequality's got reversed, because effectively what I've done is change to a negative there by doing that. It's got to be greater than log 0.1. Oh, sorry, that's not true. We're going to reverse the inequality in the next line. So we've still got that way around, because it's the log function is strictly increasing, so it will be that. It will be the next line using the rule of logs. 9 log 24 over 25 less than log 0.1. And now, because we're dividing by a negative, this is a negative amount, and it's got to be greater than log 0.1 divided by log 24 over 25. Okay, I'm working that out on a calculator. N is greater than 56.4, so n equals 20. In order for that to be the case, because we're looking for the next highest integer, n equals to 57. Okay, right, let's have a look at the final question. Okay, so we're on to the last question now. And it's a discrete random variable question, and we've got a PDF. There's a formula for finding the mean and variance. The mean, this is part A, is equal to the integral between the relevant limits. The general case is infinity to minus infinity of x fx dx. But in this particular case, obviously our limits are 2 to 0. So that's 2 to 0 of x times by 9x minus 3x squared over 10 dx. So that's 1/10 of, taking the 10 out, 2 to 0, so just basic integration of powers. That's 9x squared minus 3x cubed. So that's 1/10 of, that's 3x cubed minus 3 over 4 x to the 4 from 2 to 0. So that's going to be 1/10 of 3 times 2 to the 8 minus 3/4 times 2 to the 4. Take away, obviously, because it's just powers, this will be 0. Okay, so let's work this out. I've written that out. I've written an 8 there. Probably 2 to the 3, of course. So it's equal to 8. So that's 3 times 8, which is 24. So that's 1/10 times 24. This is 16 divided by 4, which is 12. So that's 12. So that's equal to 1.2. So that's our mean. So we turn to working out the variance. var of x, the formula for that is x squared fx dx minus mu squared, or ex squared. But in this particular case, it's equal to the integral from 2 to 0 of x squared 9x minus 3x squared over 10 dx. So that equals 1/10 of integral from 2 to 0 of 9x cubed minus 3x to the 4 dx. I've forgotten to take away the mean, which is 12 over 10 or 6 over 5 squared, 1.2 squared. Take away 6 over 5 squared. So that equals 1/10 of, let's integrate that, that's 9x to the 4 over 4 minus 3x to the 5 over 5 from 2 to 0 minus 6 over 5 squared. Okay, when we work that out, when we work all that out and put it in the limits, let's do the first line, 9 times 2 to the 4 over 4 minus 3 times 2 to the 5 over 5, take away 0 again, take away 6 over 5 squared, that all comes to 0.24, which will be the answer. That's what we're looking for. Right, let's turn now to part C. Probability that x is greater than 1.5 is going to be, now we're just integrating the PDF, between 1.5 and 0. So that's 1/10 of, and 9x integrated is equal to 9x squared over 2, and 3x squared integrated is equal to x cubed from 1.5 to 0. So that equals to 1/10 times by 9 to the 1.5 squared over 2 minus 1.5 cubed. Again, the 0 is not going to give us anything, so we're not going to have anything from the 0, so I'm going to leave that bit out. 0 value doesn't come to anything. So if I work that out, that comes to that's going to be equal to 0.675. So sorry, I've got the inequality the wrong way around. That's going to give us that amount. So that we want 1 minus that, so because we want the probability that x will be greater than 1.5. Just by changing it to that, it meant the numbers are easier to work out. Which is equal to 0.325. Okay, right, so now finally we're getting close to the end of the paper now, and again they've tried to mix it up again towards the end. They said Peter raises money by collecting paper and selling it for recycle. A bin full of paper is sold for £50, but if it weighs more than 1.5 kilograms, which is what we've worked out here, okay, then it's going to cost £25. So we've now got a discrete random variable where the expected amount is like this. So if we've got, call it x, and probability that x equals x, it can either take a value of £25 or £50. Okay, now it will be £25 if it weighs more than 1.5. In other words, the amount we've worked out here, 0.325. but it will be worth £50 if it's less than 1.5. In other words, this number here, 1 minus it, so that's 0.675. So the expected value of this is basically these two numbers multiplied together and added. So it's 25 times 0.325 plus 50 times 0.675, which equals to 41.875, or £41.88 if you want to round up or down. I don't think we need to be too concerned about that. So in the long run, that's what we would get. So that's a couple of marks for that. And then for the final part, it says Peter could remove all the staples sold, but the time taken to remove the staples means that Peter will have 20% fewer bins full of paper to sell. Decide whether or not Peter should remove all the staples before selling the bins full of paper. Give a reason for your answer. Well, this is our key really. The expected money collected if staples not removed is the amount we've got here. So that's equal to £41.88 or 875, whatever. But if he removes the staples, because he's going to actually be able to only have 20% fewer bins full of paper to sell. So if expected collected if staples removed, because he's got 20% fewer, you'll make 20% less. You'll get £50 for them, but there will be 20% fewer, which is 0.8, 20% fewer bins. So that's £40. So therefore, because £41.875 is greater than £40, Peter should not remove staples.